Hello and good afternoon. My name is Farid Pasha, and I welcome you all to my presentation today on how to perform machine learning tasks in the Wolfram language. Before I start with demonstration, I want to point out that Wolfram Research has pioneered highly automated machine learning and has deeply integrated it into Wolfram language. With the release of latest version 12.1, Wolfram language pushes further in the direction of having fully automated machine learning capabilities for every task. So, having said that, you can use machine learning in automating human judgment tasks, or it can be used in making decisions by developing models that predict sales, forecast, or finding consumer patterns. Either you are interested in developing a machine learning algorithm for recognizing or identifying objects or finding or detecting anomalies in data or even developing embedded intelligent systems, you can use the Wolfram language to develop such machine learning algorithms. So let's start with some types of the learning algorithms available. They differ in their approach, the type of data they output and input, and the type of task and problem they are intended to solve. So basically, I have divided them into three or four basically main categories. They are like supervised learning, which is the most common task, most commonly used. And how it works, it builds a mathematical model of a set of data that contains both the inputs and the desired outputs. The data is known as training data and consists of a set of training examples. Each training example has one or more inputs and a desired output, also known as supervisory signal. Unsupervised learning algorithms take a set of data that contains only inputs in the data. Oh, it should be only inputs. Sorry for the mistake, only inputs. Uh-oh. And this is getting very famous these days because of the labeled data is getting very expensive these days. Third scheme can be active learning, or often referred to as semi-supervised learning or reinforced learning. This paradigm is not yet common in industry, but lots of research is being carried out. The definitions and techniques in this category are still fluid. Last but not least, neural networks. This is inspired by how the neurons works in human brain. Before we look at each of them in detail, let's summarize and see what Wolfram language has to offer for you. So Wolfram language offers automatic machine learning framework. So most of the functions are pre-built, available, and we will take examples of each and every function during this presentation today. But I want to point out there, they are very easy to use, they are task-oriented, they are automatic, and they can be implemented on wide range of data types, which can be numerical, image, text, or even audio. Similarly, neural network framework is available, which is model-oriented, it is highly flexible, and you can use GPU training to get high performance or even out-of-code training. Then there are many built-in machine learning functions like classifier, image identify, facial features, text cases, which are available within the Wolfram language, which you can start using right away. So let's dive deep into each of these categories and see how they differ and how you can use certain specific functions of Wolfram language for it. So let's start with supervised learning. Supervised learning algorithms consist of two major tasks that are classification and regression. Classification algorithms are used when the outputs are restricted to limited set of values. And regression algorithms are used when the outputs may have any numerical value within a range. So classify and predict are main built-in functions in Wolfram language that automatically select and build models using labeled input. Both these functions can be used on many types of data, including numerical, textual, sounds, images, as well as combination of these. And I will be showing you examples of how to use them as well. So let's look at classification first. So in the task of classifications, we have to figure out a label for the given sample in the training data, and which has already been labeled. So in this case, we have age and income as the features, and the label is yes or no. So whether or not they possess a credit risk. Here we have a list of such data points, and a classifier is trained on this data. By training, I mean we infer a function from the data which map a feature value of age and income to the label. So when I pass the function a new data point to the classifier function, like the age 35 and the income 65, it can return a predicted label which can be yes or no for credit risk. So how can we accomplish this using Wolfram language? So the main function for classification, as I mentioned earlier, is classify. I want to emphasize here again, stating that it can be used on many types of data. So here is an example of using this function on a toy data set which contain images. So I have the images of cats and dogs which are labeled correctly as cat or dog, and I feed this data into the classify function, and now I get a classifier function. And now when I use this classifier function and give it any image, it should give me a label. So in this case, it tells me that this is a dog. Let's look at another simple example. Again, a toy dataset which has numeric feature set and a nominal feature, which in this case is a color. So the numerical feature set are just numbers that varies from 1.5 to 12.4, whereas the nominal feature set can be blue, red, green, and each sample has been given a label like A, B, or C. So once this input training data has been fed into classify function, I can get a classifier function built out of this. Now I can use this classify function to make certain decisions. So for example, if I pass it another value 10.1 and the color blue, and I ask the classifier to predict the label for this data, and it returns that the class of this data is probably C. But I can see the probability of this data as well. So maybe I can ask it like, let me say C, which is my classify function, and I say, okay, 10.1 and blue, and I need to see the top probabilities. So I can call the top probabilities to get the values out of it. Or I can ask the probabilities of all the classes. So if I just give probabilities, it can give me the probabilities. So this way I can use the classify function to get some details from it as well. Now, classify function by default tries to choose a good algorithm for the task in hand. However, it is possible to customize Classify according to your own needs. If you have a particular problem in mind and you have some idea about the data that you are going to work with. So there is flexibility where you are free to choose a particular algorithms. So Classify function in Wolfram language allows you to select any one of the many well-known classify algorithms like logistic regression, nearest neighbors, sport vector machine, neural networks, Markov, or decision tree as well. So in my today's demonstration, I'm just showing the very basic functions that you can use for quick machine learning tasks. I remember we have already given a task on the neural networks, which is also available and posted in my playlist over there. So let's take a look at an example of how Wolfram language chooses which specific model on that. So let's take some sample training set. So this data has just one single feature and a label corresponding to it. So for the feature value of 1, it has the label A, 2 has the label A, 3 has label B, 4 has A, again 5, 6, and 7 has label B. So let's train this function, and at this time, what I'll be doing, I'll be specifying a method. So I'll force Wolfram language to use a logistic regression method to train this classify function. So basically, I'm controlling the process here. Now, let's use the same training data set, and this time I will control Wolfram language and say use a specific method called knife base. And then when I have these two, I can also compare the class probabilities of the two classifiers. So the blue line shows the decision based on logistic regression, whereas the orange line shows the decision based on knife-based method. You can notice that when using logistic regression method, the result varies very smoothly or more smoothly, whereas with knife-based method, you will have higher probabilities when the input feature set is less than 4. But once the feature set is greater than 4, then the probability falls. So this explains that based on your dataset, you sometimes may want to use a specific algorithm, and Wolfram language provides you with that flexibility. Similarly, you can also use utility function, which can be used to customize the classify function. This allows you to specify a utility function for predicting each class correctly or incorrectly. More details on how you can specify it can be found in Wolfram Documentation Center. Similarly, you can also set the performance score, which can be used for optimized of training speed, actual runtime speed, memory usage, or accuracy of predictions. So let's move forward to a different kind of supervised learning task, that is task of regression. So in classification, for a given feature set, we were trying to predict the labels of new data point. Whereas in regression, what we try to do is compute a target value. So similarly, in case of classification, we were trying to find the credit risk, where in regression, we try to predict a corresponding credit score. So in the training data, we have similar feature set, which is age and income. However, in the target, we now have a numerical value. So the idea is now to infer the function from the data that maps from the feature values to the numeric target. So given a new data point, a regression function is used to compute a target value that is optimal for the given features. So now if I give the value of age 35 and income 65,000 to this specific classify function, I will get a predicted target value of the credit risk. The main Wolfram language function for regression task is predict. And here I show a very simple example. So here is the training data, where the feature set consists of two values, a numeric value and a nominal value, which in this case is a character. Each feature set then have an associated target value mapped to it. So here, once I have trained the function, I get the predictor function over here. It tells me what was the input type, the method used, and the number of training examples used. So once it's trained, I can pass a new data set which has a numeric value of 1.8 and a nominal value of q, and then I can get predicted target value. So the same way we were able to customize the classify function, Wolfram language offers the same flexibility in predict function as well. While linear regression is the most commonly used regression algorithm, but predict function can internally use other algorithms as well, like nearest neighbors, neural networks, random forest, Gaussian process, etc. So using this small training data set, let's see how different algorithms behaves on this. So here is my training set. And then I train this predictor using the linear regression method. And then by using the nearest neighbors method. And once we have the predictor functions available for both methods, we can compare them to see how the target values differ from each predictor functions. So linear regression versus nearest neighbors function. Similarly, utility function and performance goal can also be used for customization of predict function. Okay. Once you have created a classifier or predictor function, you will also be interested to extract information about the parameters of the model. I will quickly demo how to see this further information. So, as always, I'll start with an example. So let's train a classifier on this training dataset. And for this demonstration, I'll be using support vector machine method. So once I have the classifier function C, I can get information about this, information C properties, and I can get information about this. And here is the list of properties I can get. For the support vector machine method, we are specifically interested in parameters like kernel type, multi-class strategy, soft margin parameters, and gamma scaling parameters. So we can find the values of these specific parameters by selecting a feature called options, mapping it to all of these kernel type, multi-class strategy, soft margin parameters, scaling parameter. Did I miss something? Let's see. So we have the classifier function. We can have the properties. We can have classifier information properties. So this is obsolete. I know that. Let's see if that works. Okay, I'll check what's happening over here. Otherwise, what should do? It should give me the values for this specific parameters over here. And then I will be able to retrain the classifier based on that information. So I will give those as an option, and I will be able to then retrain this. And you can see by retraining those parameters, previously I was able to improve the training time of my system. So you can see how drastically the training time has reduced over here. Similarly, classifier movements allow the movements of variety of performance matrices for a classifier as well. This example demonstrates some of its capabilities on an image classifier. So let's train a classifier function using the images of trees, and here is a training set where we have images of trees with the feature set values of map to their type. So we have images of eucalyptus, maple, pine, and oak trees. And then we can have the classifier monuments for that. Okay. My system has been doing very strange things today. So, and then I'll have the report for this as well. So let's put together a test data report, and it will be used to evaluate the performance. So we can dig deeper, much deeper, and find also two best classified sets by mentioning over here. You can also extract the worst classified examples. And check their classification as well. And you can see here that as per classification model, they shall be classified under oak in test dataset, whereas we noticed that they were classified as eucalyptus and pine trees. Here you can obtain all test examples which were misclassified as oaks. And you can also then calculate the F1 score and the Matthews correlation coefficient along with their uncertainties. Let's move forward, and I will try to cover the functionality related to unsupervised learning in Wolfram Language. So unsupervised machine learning algorithms infer patterns from a dataset without reference to known or labeled outcome. Unsupervised machine learning methods, you cannot apply them directly to regression, or a classification problem because you have no idea what the values for the output might be. So that makes it impossible for you to train the algorithms the way you normally would. So these are used instead to discover the underlying structure of the data. Clustering and association are two types of majorly used unsupervised learning techniques. So let's get started with clustering. So find clusters is primarily the main function in Wolfram Language, and it helps you to find clusters, and it can partition the dataset into clusters of similar elements, and it can handle all sorts of data, either it's numerical, textual, image, or as well as dates and times sometimes. So we have a list of numbers of functions available, and we'll try to cover most of them over here. These are all the functions which are available in Wolfram Language, and I will try quickly to cover as many as I can in the half an hour left with me. So let's get started with clustering. So we have a list of numbers, and here we try to find the clusters in them, and we see that it finds two natural clusters, one of the numbers less than 0 and one of the numbers that are greater than 0, or the positive integers and the negative integers. In the below example here, we specifically can also explicitly specify the numbers of clusters we like to find. So here we specify that we want like 4 clusters to be found, and so we have the result where the numbers is partitions into 4 clusters, and this is what we get. clustering components. Another function that can be used to find clusters, but which differs from the find cluster function, is the clustering component. So in find clusters, we get a sub list which represents the clusters found in the data, like in this example. Whereas in clustering components, what we get is the index of the cluster, not the values itself, but index to which its sample belongs. So here in this example, you see the find two clusters and showing two groups of numbers in two different clusters. Whereas clustering components find similar cluster, but when it tells us, it gives the result in the form of the index of the cluster to which it belongs. So 10 and 11 belongs to cluster 1, whereas the values 4, 5, and 6 belong to cluster 2. Similarly, nearest. So this is another function that can be used in a similar way. So it finds the element closest to the given sample. So here I have a list of numbers, and I want to find number that is closest to my sample, which is 8 in this case, and it will give me the number that out of this data points, the closest number to my input value 8 is 10. So we can also find 5 data points to 8, nearest to 8, by mentioning in this way. Similarly, we can also customize how the clusters are found by find clusters function, and here I will show you 3 possible options. Note that there are many other options that you can specify for find clusters, and for that I would encourage you to look at the documentation page for find clusters to learn more about that. Here I talk about 3 different options. The first one being the distance function. So by specifying the distance function, we can ask the algorithm behind find clusters to use a particular distance function while finding the clusters. So as you know, for clustering, what we are trying to do is group together elements that are near each other and separate elements that are farther away from each other. And this notion of newness and being far away has to do with the distance between the elements and how do you find the distance between the elements themselves. So what you have to use is distance function. So a very common distance function is the Euclidean distance, and it is very useful when you are dealing with your numeric data. However, if you are using something like Boolean data, then checkered dissimilarity might be more useful. And for things like string data, the edit distance or the Hamming distance might be more useful. So here I show a made-up example. So suppose you have some data points as shown here in the picture, and what would be a good distance function to use? Well, in this case, we can see that if we use Euclidean distance, the clustering is something like this, which is obviously not what we would like. Notice how the 3 different color points are still mingled together. However, if we use cosine distance, then the clustering is much more appropriate. And you can visually see that here. Second option that I wanted to show you was method. And by changing the method, you can use certain clustering algorithms which might be considered to perform better than others, depending on the natural clusters in the data. So here again is some example data, and as you can see that there is natural cluster here in the center, and then there is some sort of noise around it. If we just use regular k-mean clustering method, then what happens is it ends up dividing the main cluster into two different parts, and that is not really what we want. However, by setting the method option to density-based scan or density-based algorithm for clustering, we see that it has done a much better job of identifying the central cluster and separating it from the noise that is surrounding it. Okay. So the third option that I would like to discuss today is the criterion function. So by setting the criterion function option, we can change what is given importance in identifying how good the clusters are once the clusters have been found. And so here again in the artificial data set, we have really two natural clusters. And we can see that if we use the standard deviation as the criterion function, the outer ring is broken up in many different clusters. However, if we use a specialized Kalinske-Harbach index as the criterion function, it does a much better job of separating the two clusters. Of course, it's still not perfect, but it is definitely much better than using standard deviation. The Wolfram language also offers many different functions for quickly visualizing the clusters. The clustering tree, for example, quickly provides a weighted tree from hierarchical clustering of data points. So for example, if I have 30 random colors, I can use the clustering tree, and it has the ability to pick up many different options. So in the below example, see here I am mentioning the cluster dissimilarity function to be option to be as a centroid, and then I have a different clustering tree because this particular dissimilarity function was used. Similarly, dendrogram function also creates a tree. However, dendrogram is commonly used for visualizing a tree where the heights of the nodes are proportional to the intercluster distances. And again, I show an example of the dendrogram using the cluster dissimilarity function as centroid, and this is the sort of clustering that is shown by the help of the dendrogram. Okay. Clusters can be seen as potential classes in the data as well. So in the absence of pre-labeled training data, where we don't know which class each data point belongs to, we can use clustering as the basis for assigning some sort of labels to the new samples as well. So let's try a simple example here. We have a list of numbers that we have looked at before, and now we use the cluster classify function, which builds a classify function similar to the more commonly used classify function in the Wolfram language, which does supervised learning. So now that we have the classify function, we can get more information about it. We can see which method is used. So in this case, agglomerate model method was used while building this classify function. It also lists the training examples used, 8 in this case, and it found 2 classes, rather 2 clusters, which are the basis of these 2 classes. So now we have this classify function. We can use it to cluster classify new samples. So basically, we can use this for labeling of the new data points. So for example, here we asked to classify -4 and it's from the second cluster, so we can give it a label 2, and then 10 being from the class label 1, which is the first cluster. Let's take another example. So here's another example. Here I'm using the data by generating some 50 random colors, and then by using cluster classify function as the on this data set, a classifier function is created. And you can notice over here that it automatically used the k-means method and returned 3 classes because I asked for 3 classes. And then now I can pass some other sample data points to this classifier function. And it is interesting to note that I do not have to provide the input again in the same format. As you can see that the input was given as RGB color values, whereas in my below query, I'm simply writing the color name. This is due to the fact that Wolfram Language understands the RGB description of the colors and will give me the corresponding classes for each of my sample data point. And in this way, I can start labeling all those data which is not yet labeled. So this is a very good way to generate labeled data set, rather than, because we know that the purchase of a labeled data set is always expensive. So we can start with a small data set which is labeled. Based on that, we can get the clusters, and using those information, we can start labeling those data which is unlabeled yet. So let's move forward. And here is another useful function available in Wolfram Language, which is find distribution. Given a large amount of data, what it allows us to do is create a very simple interpretable model of how the data was generated, what sort of distribution does it comes from. And the advantage of this, that for a list of possible outcomes from a univariate distribution, this find distribution function attempts to learn the continuous or discrete distribution from the data itself. So let's explore a bit further by using this example where we create a mixture distribution from an exponential distribution and a normal distribution with mean 5 and variance 0.8. So let's build the distribution and then randomly sample this distribution to get data, and we can see the histogram. And from the histogram, we can see that we really see a mixed distribution. Now we try to find a simple distribution to fit this data by using the function find distribution. And we can actually compare the fitted distribution to the histogram as well by plotting them together. And we can see that it did a reasonably good job of fitting the data. Now we switch gears and move on to feature space. The idea here is to automate the process of extracting useful features from raw data. So given any sort of data, feature extract is a Wolfram function, language function, that can transform it to numeric vectors. And why would we do something like that is because once we have the numeric vectors, it becomes so much easier to find distances between samples, and finding these distances is the primary requirement for doing clustering or k-nearest neighbors. Also, once you have numeric vectors, it becomes easier to apply transformation like standardizations or transform on it, affine transforms on it. So let's take an example. And again, similarly, the feature extract also works nicely on all data types. Here is an example of implementing feature extract function on the image data. So now, once we have the numeric vector data, we can use it for other machine learning functions. Wolfram Language also have a feature extraction function that can be used to create a function of feature extractor. So now you have the function, you can use it on other samples which has features like the training data and get the corresponding numeric vector. So another very important aspect of working in feature spaces is that when we have features that have high dimensionality. So what does dimensionality means? We have too many features and we need to project the data to lower dimensions. Wolfram Language has a function called dimension reduce to avoid curse of dimensionality, and it allows intuitive visualization of data points in both 2D and 3D. And of course, when you are dealing with less features, it allows for the models to be more easy and interpretable. So let's take an example here where we have strings and we can use dimension reduce without any specific options. So it goes through this string and then results is in only 2 features. Let's take an example of exploring this feature space. So we construct a data set of dog images. So we have a data set of images of dogs. And from these images, we can use the feature extract on this data set. So I get the numeric vector values of them. Then I can reduce the dimensions to vectors by 2. And you see I'm using the TSNE method over here. So I reduce the dimensions in 2. So I get less dimensions to deal with. And then I can visualize the images at their feature positions. So based on their feature positions, I can have a feature space plot of that. So in Wolfram Language, we also have a built-in function which can do all of this task above, which is feature space plot. And by doing that, you will get this thing automatically rather than performing all of these functions over here. So we can have a feature space plot. Let me run this data set, and then I can have the feature space plot of that automatically. So this function is built into Wolfram Language. So these are some of the functions in Wolfram Language that I have covered, which are related to unsupervised learning. There are many more functions available, which I could not cover in just 1 hour, but I encourage you to explore machine learning tutorial, which is available in the documentation center. So now let's move quickly along talking about learning from actions and sequences. I will quickly outline why semi-supervised learning is useful, and then we'll demonstrate 3 main functions that are available in Wolfram Language. Like I'll be touching about active classification, active prediction, Bayesian minimization, and sequence predict as well. Okay, so why are we interested in semi-supervised learning? And the major reasons I already told you is that it can use both labeled and unlabeled data for training the model. Now, labeling is expensive as well as time consuming, and it also requires domain expertise. So you need to find someone who must have enough knowledge of the domain so that they can label correctly all the data quality of the training data definitely affects the quality or the ultimate performance of the machine learning model. So where labeled data is expensive, whereas on the other hand, it's much easier to obtain the unlabeled data. So the idea of semi-supervised learning is that we start with a small set of labeled data, and then we keep adding data from the set of unlabeled data. So we augment the training data set. So active learning is a specific class of this semi-supervised learning algorithm, which allow to query the user of the algorithm to label a subset of the unlabeled instances. It is an iterative process, and the learner requests the user to select few examples in each iteration. This process is repeated till the convergence is achieved. Now, by selecting smartly, once a small amount of unlabeled data can be used to get a very good performance. So you don't need to label the huge set of data to get a good training set. And there are a number of different query strategies like uncertainty, sampling, query by committee, randomized sampling, and information-based sampling that are commonly used. So let's take a look at active classification, which is an active prediction, which are the two main functions used in Wolfram Language for active learning. They both use classifiers and predictors by actively sampling a space. Internally, they are used to optimize all sorts of meta algorithms that are built into the Wolfram language. So the syntax looks like this, where you have the active classifier classification function, and then the arguments are the function f, and you need to provide the space spec. And by doing that, what it will try to do is find the best classification or prediction model by using this function f to determine the classes and values for various configurations provided by space spec. So how you define the space spec? There are 4 different types of domains for this function. It can either be a list of configurations that active classifier function can explore, or it can provide geometric region, or you can have a configuration generator or sampler, or finally you can have a list of initial configurations together with the neighborhood configuration generator. But you need to make sure that the output of the neighbor sampler shall be such that the function f can be applied to it. So this is the basic requirement for this. And these configuration can be of any type. You can use numerical, nominal, text, sounds, or images as well. Maybe I need to show you one more thing. Yeah, okay. So by doing this, what the output will be generated by active classification or active prediction is in form of an object with a lots of information and properties which you can query. And in the next slide, I will show you some properties, how they are available and how you can utilize them. So let's take a simple example to understand. And here we work with the data of the passengers of the Titanic ship. So we get the training data. So we're going to build a classifier to classify the survival status of the passenger. So we start by developing the Titanic oracle. So once we have the data, we can see it contains of like the class in which they are traveling, age, and their gender, and a corresponding label if they died, survived, or in the accident. So the next step will be to develop the Titanic oracle. So what I'm doing over here is just a lookup function where if I give a combination of class, age, and the gender of the passenger, then it will try to find the occurrence of such data points in the training data set and look up for the provided model. So let's just test it with some configuration like passing the category, the age, and the gender, and it gave me the label for that. So now the next step will be to create a configuration generator. And this is the second parameter that is to be provided to the active classification function. So the configuration generator here is just a random sampler of the training data. And then we can use the classification function over here. So it constructs a classifier. So now once we have the classifier, we can do certain queries on it, like the properties of like the training history, classifier function. So in the first here, I'm looking at the training history, and you can see it started with how many samples it applied on each method before making a decision to continue with the method or to choose another one. So this gives a very good snapshot of the training history. We can also look at the learning curve. I can also evaluate the classifier function that I have created. So we construct the test by generating a test data set from the same data set and then look at the confusion metric plots. So you can develop a model like this. Similarly, this is for active classification. You can also do a similar example for active prediction. I'll skip this example to save some time to cover my next slide, which is more interesting on generative learning. But I'll give you the access of my file, and I will encourage you to evaluate this example. This is very self-explanatory, and you can contact me via email if you have any questions on this as well. So let's take an example, quickly demonstrate on the generative learning. So using this in Wolfram Language, you can train a sequence predictor on a set of sequences. So in this example, what I'm doing is I have a sequence of images for paper and rock and scissors, gestures, and we will use it to train a predictor to get the next elements in the sequence. So this one is used as a training set. So we can use this to train the model. So once the model is trained, and I can see which method it used, Markov over here. And once the model is trained, I can pass in a new sequence to predict the next outcome. I can also obtain the probabilities of the sequence to occur. And more interestingly, it can also be used to predict the most likely sequences. Means I do not only want to get a next event, but also can predict the outcome preceding the next event. So in this example, I want to see the next two possible upcoming events to happen given a certain scheme. Okay. So the next is about the built-in features available in machine learning, which are available in Wolfram Language. So you all must be aware of the image identify machine learning function. So whenever you pass up an image to this machine learning function, it will try to give you the corresponding label for that. So I'm using the image of a gray wolf over here and pass it to image identify, and it tells me that this is the gray wolf. Similarly, if I pass on any other image, like some lemons, and it tells me what it is. So this was also, this image identify function was there in previous versions in, I think, 11 also. But in version 12, what we have done is we managed to generalize this. And you only don't get what is in the picture, but you also get what other images are available. Like I can use another function called image cases, and it will tell me where it has elephants and it has zebra in this image. Similarly, I can also use a built-in function called image contents to get where that specific object is available. and I can also ask them to test if my image contains any particular kind of object in that specific image. So using the same technology, we have another function called find faces. So if I pass in an image, and I can have a find faces function implemented on that, and it will identify the face in that specific image. Similarly, we have recognize noble persons. So if you have an image of a notable person, you can pass that into classify function, and Wolfram Language will try to get this data of this celebrity if it knows about that from this using machine learning. So notable person classifier function is already available, and you can also implement many options or properties, like I can get what is the probabilities that this image belongs to a specific person. So I can get that there is like 25% chance that this is Joseph Mengele, but still there is like 6% chance that this can be Richard Nixon. So the concept of machine learning is not to get an accurate result, but it will tell you if it works. Similarly, we have a function called text structure, which you can call Wolfram Language, and once you utilize this machine learning function, it will try to infer more information from this string value. So it will try to give more details that the house is blue, is this is a noun phrase, which a verb, is it an adjective or adjective phrase. So you can implement this on string also. So as I mentioned earlier, machine learning functions in Wolfram Language can be applied on many types of data types. Similarly, you can also utilize the language identify built-in function, which automatically tries to identify what the language is. So if you pass on different languages, it will try to identify which class or what is the correct label or classification for a specific input over here. You can also do some speech capture. I don't know if I'll be able to show that online, but let's try. So I'll try to do this by recording something. Hello, computer. How are you doing? Thank you. So I can have the audio capture over here. So once I have this audio, I can see the spectrogram of that, or I can use the built-in speech recognize functionality, and then it will try to analyze based on my input what I have tried to say in English, and will try to give. So hello computer, how are you doing? Thank you. So in this case, it has done a very accurate job to do that. So there are certain other languages which you can use, and not for exactly for speech recognize, but you can use that for audio analysis in other languages as well. I do not have an example right away over here, but I can show you sometime later. Similarly, there is a sentiment classifier function also available, which you can use readily. So you can pass on some phrase like, I love this movie, so depressed, or my phone broke down, and the sentiment classifier function will try to classify if it is a positive or a negative comment. This has been developed using, I think, most on the, also can be used on finding the spam, applying spam filter, or using all those on text structure analysis as well. So this was the quick overview I can give in just 1 hour. I think I exactly used all of my 1 hour over here. Thank you for being with me. If you have any questions, feel free to write a comment. And in next few minutes, I look through the comment box, and I'll see if there are any questions over here, and I'll try to answer them. So if you have any questions please do tell me. Please contact the Hanif if you have any questions. Okay, so let me know if you have any question. In the meantime, I wanted to show you one more thing. I'll try to find it where it is in my system in the meantime. And once I'm able to get that, I will show you, and I'll also look at the questions also. So I have one example which I wanted to share with you, which was more on the feature detection used in a real life project. So I'm trying to show you if I can share something over here. So let's see if I'm able to do that. Okay. So excuse me, is it possible to learn machine learning of big data composed of 4 combination? Is it yes, you can use more. In the simple example, I only showed 2 combinations. If you have more combinations, you can also use those as well. So for example, in this, let me see how I can remove my picture from here. So maybe I'll try to. So this is an example I wanted to share with you. So this is using real-time, not real-time, it is using images and using machine learning criteria on top of that to see if the crop is infected or not. And I think it is also giving the corresponding probability of how much infected this crop is. So this is a good example. I could not share more details about the customer and more about this project, but I could only share you the specific pictures over here. So you see how you can see you can have an image, and then you can apply certain types of machine learning technology on top of that to find if the crop is infected or not, or what percentage of the crop is infected. So I think this is a very good example of how it can be used in some fields, like even in agriculture, because at the end of the day, it is all about image analysis, and because Wolfram Language can take the image as an input functionality and perform certain types of analysis on top of that. So similarly, you can also do quality prediction. So maybe if you have a data set of certain wine, and there are certain examples, and you have certain criteria, you can do certain types of testing on that, and then you can also have the quality visualization on the range of pH value and other parameters and the factors, and you can find more details using machine learning techniques on that by training the model and testing the models. So this talk is more highly advanced. So now we have covered the basic of the machine learning. So in the upcoming weeks, most probably I'll set up something more advanced, in which we'll go more deeper into how to utilize that on some real life examples. Similarly, on the Patreon, I have did the data visualization courses, in which I have took the real life examples. I will be doing another session which will be more advanced and performing Wolfram capabilities on the real life. So stay tuned to that. If you have not subscribed, subscribe it, because normally now we do not send any specific invitees to attend the session. Let me quickly look at the examples. Any more questions? So if we have no more questions, we can close the session over here. I want to thank you. I would like to say thank you for being with me again today, and it was really nice to share some details. Because machine learning is such a vast topic, it's very hard to confine all of that in 1 hour. But now you have machine learning basics. I have already given the neural networks, which was like step by step how to perform neural network, develop encoder, decoder, and use on specific one, you have already attended that. If not, it is available on my playlist. You can view that neural networks from there. So the next session, most probably I'll be planning, will be on developing more advanced machine learning techniques, as well as on solving equations. And another project which is in pipeline is to how to a step-by-step guide of how to develop dashboards. So these are the couple of few more projects which are in pipeline, and I will share with them in due course. So thank you everyone for me. If you have any questions, you know where to find me. You can write a comment, or you can drop